Welcome back. Today we're going to be talking about VSEPR theory, and I'm sure that you remember this from your days in general chemistry. VSEPR theory kind of talks about the three-dimensional shapes that your molecules can take when we take a Lewis structure and think about how the actual atoms bond together in 3D. In your previous chemistry classes, though, we kind of didn't tell you all of the possible VSEPR shapes because we didn't tell you about the expanded octets. And so there's a lot more VSEPR shapes than you maybe initially thought there were. So I guess, fortunate part is that they aren't incredibly complicated, but the unfortunate part is that you have to memorize all of them and their bond angles. So we're going to get into that today, but we're going to refresh what the VSEPR theory is, generally how it works, and then go from there, okay? You also, by the way, will have a chart in your book of all of the different VSEPR shapes if you want to do a little bit of practice or make some flashcards with that, because I know that it takes a lot of practice to get them all memorized. So VSEPR is an acronym, and I know it looks like VSEPR and it gets people very angry, but we say VSEPR theory just so it's easier to say. Stands for valence shell electron pair repulsion theory. And the general idea behind it is that if you think about all of the bonds that make up a molecule made up by those atoms, the bonds that occur between two atoms happen because of the overlapping of the electron shells. And when that happens, all of those pairs of shared electrons around your central atom, they're just electrons. So what they want to do is, if I take two pairs of electrons or any electrons and I bring them close together, they're going to want to push away from each other. And VSEPR theory basically says that the shape that your 3D version of your molecule is going to take is going to be the shape that minimizes the interaction that those electron pairs have to have. So what I mean by that is if you think about, I'm going to show you a picture of this guy here. So imagine that each of these lobes here is a pair of electrons. If I take a pair of electrons and I try to squish them together, they are not going to want to do that. So what they'll do is they will kind of spread out as far away from each other as they possibly can, and then that's the shape that they take. And VSEPR theory is actually a really reliable predictor on what type of shape you are going to get for your three-dimensional shape of your two-dimensional drawing. Okay? Now, when we talk about VSEPR theory and VSEPR shapes, there are kind of two words that are thrown around. There is the electron geometry. Electron geometry, there are only a few potential electron geometries. They are the way that the electrons take shape around the central atom. The molecular geometry, though, is the way that the actual bonds are located around the central atom. So what happens is the electron geometry, it's hard to say, you might hear me mess it up. The electron geometry will take its shape, but then the VSEPR shape may or may not match with that because there may not actually be a bond coming off of that shape. And I guess I'll talk about that as we get a little bit deeper. When you are trying to find a VSEPR shape, or you will sometimes see it called the molecular geometry or the molecular shape or something like that, the first thing that you have to always do is you have to draw your Lewis structure. So that is the key to doing this correctly. And on the AP exam, there's one nice thing. If you draw your Lewis structure incorrectly, but you're able to predict what your wrong Lewis structure's VSEPR shape should be, you still get the point for the VSEPR shape and or bond angle because you knew your shape well enough even though you drew the wrong Lewis structure. So you got to get the Lewis structure correct in the first place. Then what you do is you count the number of electron dense areas around your central atom only. So this can be bonded areas or it can be a set of dots, which we call an unshared pair or a lone pair. Okay. When we talk about electron dense areas, double and triple bonded areas count the same as a singly bonded area. So what I mean by that is if you are counting electron dense areas around your central atom, if you have a double bond, that still only counts as one electron dense area, and the same for a triple bond. And again, we'll go over some examples after we go through all the VSEPR shapes, and then we'll clarify. And then you have to use your memory to remember what the VSEPR shape is or the bond angle on this. So I'm going to go through each of the shapes. I'll talk about electron geometry and molecular geometry, and we'll get things going. Like I said, you should have a chart in your AP Chemistry workbook. It looks like this here. And in my book this year, it's on page 32. Okay. But that is something. So if you don't want to take notes or you want to take notes on the chart, that's totally fine. So we're going to start with the smallest possible molecules and kind of work our way up. And the chart that you have pretty much matches up pretty well with the chart that is in your workbook. So the first one we're going to look at is when you draw your Lewis structure and there are 2 electron dense areas around the central atom, and it should be 2 bonding areas, and then this should not be a 2. So cross that off. That should be a 0 here. So when you have 2 bonding areas and 0 unshared pairs, if I could get my life together here, you're going to get a linear shape, which looks like this. Okay. So if you can imagine central atom, this gray area here, that's a pair of electrons that they share, and then here are 2 bonded atoms. When you think about if I have 2 pairs of electrons, the furthest they can get away is 180 degrees. So our bond angle from here to here is 180, and that's our linear shape. Okay, linear will actually come back again at some point. All right, the next one is the 3 electron dense areas, and that gives you this guy right here. If you have 3 bonding areas and 0 unshared pairs, what will end up happening is you get a shape called trigonal planar. So trigonal planar is the idea that I've got 3 pairs of electrons pushing away as far as they physically can from each other, and they're going to have bond angles of 120 degrees. They call it trigonal planar because if you look at it, it looks kind of like a triangle. And the planar part here is the plane because it's flat. Okay, so that is going to be our trigonal planar shape. The electron geometry in this case is also trigonal planar. And again, they're probably not going to ask you about that, but trigonal planar is a shape that feeds into another shape, which is the one that's coming up next. So if you have 3 electron dense areas, but instead of having 3 bonds and no pairs, you have 2 bonds, and then imagine up here is an unshared pair, you end up in a situation where you have a different molecular geometry or VSEPR shape, but the electron geometry is the same. So the shape is still basically trigonal planar, but we're missing one of the parts of the trigonal plane. So what happens is in this case, we call this bent. So if you have 2 bonds and 1 unshared pair, you're going to have a bent shape. Now the bond angle on this is still going to be approximately 120. It will actually be a little bit smaller than 120 degrees, so slightly less than 120. And that is because the unshared pair, because it's not stuck between 2 elements, takes up a little more room and it squishes these bonds a little bit tighter. Okay, but understand that this bent and trigonal planar are basically the same, other than we're missing a bond. Okay, now the next one is when we have 4 electron dense areas around our central atom. And again, this is all based off the Lewis structure. So if you have a situation where you have 4 bonding areas and no unshared pairs on your center atom, you have a shape called a tetrahedral molecule. So if you look, trying to rotate it for you, it's called tetrahedral. Now, the reason it's called tetrahedral is because it has 4 sides if you put faces on it. So it's 1, 2, 3, 4 sides. The bond angles on this are 109.5. And the reason why they're 109.5 is because unlike our other 2 molecules where they were just moving in flat space, this has now expanded into 3D space. So this is if you have 4 bonds and 0 unshared pairs. This is probably the most common shape that carbon makes when we talk about its VSEPR shapes, but not always. Okay, now tetrahedral is kind of the electron geometry for the next 2 shapes. So when you think about it, it's like tetrahedral, but not. Okay, so if I still have 4 dense areas around my central atom, but instead of having 4 bonds, I only have 3 bonds, And now up at the top here, I have an unshared pair. I have a shape that's called trigonal pyramidal. And they call it trigonal because the bottom of it is shaped like a triangle. And they call it pyramidal because it sits, if I can do this correctly, kind of like a little pyramid here. Okay, the shape on this is still roughly 109.5 because it does have that same tetrahedral shape, but just like we saw with the bent, the electron pair up here takes up a little room, so it squishes down to a little bit less than 109.5. Okay, and there's one more shape that's based off of that tetrahedral geometry, and that's in the situation where you still have 4 electron dense areas, but now instead of having 4 bonds and 0 unshared pairs, we're going to take one more off. Now you have 2 bonded areas and 2 kind of unshared pairs up at the top. It almost looks like, if you think about looking at it head on, it'd be like Mickey Mouse ears coming off the top of here. Okay, that shape is called bent, but this bent is more bent than the other bent, if that makes sense. Not by a lot, but by a little bit. So this is, its bond angle is less than 109.5. And the reason why it's less than 109.5 is because it's born of that tetrahedral geometry. It's just missing some of the bonds. So when we talk about these shapes, tetrahedral, trigonal pyramidal, and the bent with an angle of 109.5, those are all the same electron geometry, but they have different VSEPR shapes because of the number of bonds. So hopefully that makes sense. This is where you probably stopped with your previous classes worth of VSEPR shapes. So now we're getting into the new stuff. You will see with elements that have expanded octets that their number of electron dense areas can go up to 5 and 6. And so if we have 5 electron dense areas and 0 unshared pairs, you get this crazy shape here. And hopefully you can kind of see. Let's see if I can hold it in the middle. Okay, I'll rotate it this way. So it looks kind of like if trigonal, planar, and linear merged and had a baby. It's actually called trigonal bipyramidal. So this is when you have 5 bonds and 0 unshared pairs. So what happens is you have trigonal planar and linear together. The bond angles on this are 120 degrees, which happen here. That's your trigonal planar. And then 90 degrees from the vertical to the planar part here. Okay, so this is called trigonal bipyramidal. It's called bipyramidal because technically this is a pyramid and then this is a pyramid. And it's trigonal because it has the triangle shape in the middle. So again, bond angles are 120 and 90. If I take this 5 electron dense areas and then I take one away, and I have 4 bonds and now an unshared pair up here, I get a shape that's called seesaw. So you can kind of see it's like that. Now it's called seesaw because if I put it on my hand, it can move up and down like a seesaw. Okay, so you can kind of see it looks like a teeter-totter. So that's if you have 4 bonding areas and 1 unshared pair. The bond angles on this are a little bit less than 120, a little less than 90, and then you've got the 180 here because it's completely missing that bond, okay? That bond comes off of the trigonal planar part. So this was previously here. I took that off. The reason why I take that off is because it provides me with the easiest amount of like repulsion that I'm getting rid of there. If I take one off the side where it was looking kind of linear, that does not provide the minimizing of the repulsion in the same way. Okay, so what happens then is if I still have 5 electron dense areas, so around my center atom, I've got 5 pairs of electrons, but I only have 3 bonds, then I get something called T-shaped. And that makes sense because it looks like a T. So what happens is this is your VSEPR shape or your molecular geometry. It still has the trigonal bipyramidal shape because there's an electron pair here and there's an electron pair here. But the VSEPR shape, what the actual molecule itself looks like, is a T. And the bond angles on this are incorrect. I just see it here. The bond angles on this are 90 degrees and 180 degrees. Okay, so that is just a mistake on my part. All right. And lastly, if I take this third bond off, and now I still have 5 electron pairs around my central atom, but I only have 2 bonds, what's going to happen is I'm going to get what's called a linear shape. So linear is back again. We've got 3 sets of dots essentially around your central atom, and then your bond angle in this case is 180 degrees. Hopefully you can't hear those people laughing in the hallway. They're very noisy. Okay, now when you hit 6 electron dense areas around your central atom, you get this butte here, which is called octahedral. Now you say to yourself, Mrs. Ottmeyer, this doesn't look that different. But if you look here, instead of having 3 around the center, now I have 4. So this is called an octahedral shape because if I would put a face on here, it would look like an 8-sided diamond kind of. So this is octahedral, okay? The bond angles all the way around on this are 90 degrees. If I have 5 bonding areas and 1 unshared pair on my central atom, I'm going to rip this off of here, I get a shape called square pyramidal. And this is going to look like one of those Egyptian pyramids that you're used to seeing. They call it a square pyramid because it's got a square bottom and it looks kind of like a pyramid. So what happens is we take that octahedral shape, replace one of the bonds with an unshared pair here, and the bond angles are going to be approximately 90 degrees. Okay, they might be squished a little bit, but they're close to 90. And then the last VSEPR shape that you need to know is if I still have 6 electron dense areas, so I start off with my octahedral shape, but now 2 of them are unshared pairs and only 4 of them are bonds, what you get is a shape called square planar. So it's square because it's got that square base to it, and it's planar because they all sit in the same plane. Bond angles on this are 90 degrees as well. Okay, there's lots of VSEPR shapes, and these new ones are kind of tricky. For whatever reason, people really struggle with the trigonal bipyramidal group of them, so you have to be careful. Okay, we're going to go over a couple examples. Pardon my blurriness. These are from your homework 2.2. So if we take a look at ClO3-1 here, when we are trying to figure out a VSEPR shape, you only pay attention to the central atom. So I don't really care about what's going on with the oxygens. I only care about what's going on with the chlorines. So what I'm going to do is I'm going to take a look and count my bonded areas and my unshared pairs. And in this case, I have 3 bonded areas and 1 unshared pair. So that means, let me see if I can find my parts here. My electron geometry starts off as tetrahedral, but I go to trigonal pyramidal for my shape because of this unshared pair at the top here. So it's trigonal pyramidal for its VSEPR shape or its molecular geometry, but its bond angle is a little bit less than 109.5 because this electron pair at the top squishes it down. Okay, let's go over to this Cl2O over here. So this is actually probably one of the most common ones that people get wrong because they will ask you to draw this Lewis structure and then they oftentimes don't ask you about the VSEPR shape. Sometimes they do, but they'll ask you about the bond angle. And most people draw this as a straight line. And so you say your bond angle is either, I see 180s for answer and I see 90s as answers because people are like, oh, well, it's a 90 degree or it's 180 degrees from this bond to this bond. However, stop and think about it. Gosh, everybody gets this question wrong. So if this is oxygen in the middle, according to my drawing, there are 4 electron dense areas around there. There are 2 unshared pairs and 2 bonded areas. So think about that. It starts off as tetrahedral, but I remove 2 of these. And so I do not have a linear shape with a bond angle of 180. What I have is a bent shape with a bond angle of less than 109.5. So that is an incredibly common mistake people make. Some of you will make that mistake, but try not to. Okay? If we take a look at IF4-1 and we look at our correct Lewis structure, iodine is in the middle and it has 4 bonded areas and 2 electron pairs. So that means that we have 6 electron dense areas. I'm going to put my model back together. which means that the electron geometry looks like octahedral. And then I take away 2 of them and I get a shape of square planar. Bond angles on this are 90 degrees. So from the iodine to the fluorine here, bond angles are 90 degrees. Electron pairs sit on top and bottom. Okay. And then the last one, SiO2. When I look at SiO2 and I see that there are 2 bonds coming off of the Si in one direction and 2 bonds coming off of Si in the other direction, I look and initially like, oh, there's 4 pairs of electrons. However, like I said in the beginning, when there is a double bond or a triple bond, it only counts as 1 electron dense area. So on silicon, there are 2 electron dense areas because these electrons here that are in the double bond are kind of stuck in the same place. So there's 1 dense area and 2 dense areas here, which means no dots. And that means my shape is going to be linear and my bond angle is 180. Okay. Hopefully this clears things up. It stinks that you have to memorize them. I totally get that. So it would probably help a lot of you to make some flashcards and practice these. And then we will hopefully get a little bit of practice as you go along with your homework. If you find yourself struggling, please contact me and we'll get things figured out. Good luck.